we next turn our attention to some applications of integration. So we've learned some basic techniques for evaluating integrals, and now we're going to look at some applications of integration, and there are endless variety. So we're going to look at some of the most common ones in the same way that we looked at some common applications for differentiation. Now, we have repeatedly looked at velocity and position. And that's in large part because those types of fundamental physics problems are what kind of motivated and led to the development of calculus in the first place. All right. So one of the reasons these types of things seem like natural applications of calculus is because, well, they kind of are. They really are what kind of prompted the development of calculus in the first place. So let's look at velocity and net change in this first section of chapter 6, 6.1. Let's consider we're driving along a straight highway, and we've seen this set up before, right? Driving along state highway, our position relative to a reference point or the origin will be s of t for times t greater than 0. So s equals 0 is zero displacement. S at a would be our position at t equals a. Our position at t equals b would be s of b. And so the displacement would be simply s of b minus s of a. Okay, that would be if we moved, say, if the frame of reference was such that to the right of the origin is positive displacement, then our displacement would be greater than 0. If on the other hand, our position at time t equals a was, say, here, and our position at time t equals b, where b is greater than a, as before, is here, s of b less than s of a, then the displacement s of b minus s of a would be less than 0. Okay, so far so good, right? If s of b is greater than s of a, positive displacement, s of b less than s of a, we have negative displacement. Now let's look at the velocity of the object at a particular time, and let's consider, right, we know that if this is our position function s of t, that our velocity function is s prime of t, which means that s, of course, is an antiderivative of v. So if I were to integrate from a to b, my velocity function, that would be the integral from a to b of s prime of t t. And we just saw that since s is an antiderivative, right, the integral of s prime should just be s, so that would be s at b minus s at a. Okay, and that's our displacement. So we see that the definite integral from a to b of v of t dt is the displacement. It is the change in position between times t equals a and t equals b. Okay, or equivalently, geometrically, if I look at the graph of the displacement, the velocity function. So if I look at y equals v of t, the velocity is a function of time, then that displacement is simply the area underneath the velocity curve. Okay, the displacement from A to B of an object with a velocity function v of t is the integral from A to B of v of t dt. Okay, so in a case like this, right, you see the definite integrals of displacement times t equals A and t equals B. We see it's a net area. So in a case like this, right, the displacement would be A1 minus A2. If one, if part of the area is negative, again, it's the net area here, net area of both, since both pieces are positive. Now we're looking for this, so this area function. Now if we're going to look at the speed, and so let's caveat this with, so here we have y equals v of t, the displacement here, a1 minus a2, it's that integral from a to b of v of t dt. That is not to be confused with the distance traveled. The distance traveled is asking you to look at the magnitude of the velocity function. And so that the distance traveled would not be a1 minus a2. You would be looking at the absolute value of the velocity of the velocity being the speed function. And that would be the integral from a to b of the absolute value of v of t dt. And so let's roll all of these together in some definitions for position, velocity, displacement, and distance. Okay, now we can think of, right, these should make intuitive sense. Displacement versus distance in particular. So let's consider, let's consider displacement. Suppose I get in my car, I drive to the store, and then I drive back to my house. Okay, well, my displacement would be 0. My displacement would be 0. But the distance traveled would definitely not be 0. Right? I'm going to have burned gas going from my house to the store and from the store back. Right? So that's the difference between displacement and distance. Let's consider now an example. Suppose I have a jogger running along a straight road, and the velocity in miles per hour of this person is given by v of t equals 2t squared minus 8t plus 6. The first thing we want to do is we want to graph the velocity function over this interval 0 to 3. And we want to know, when does the jogger move in the positive direction? When do they move in the negative direction? Here, I can graph the function. So it's just graphing that quadratic, and that is going to look like here. Okay, so here's the graph. So when are they moving in the positive direction? They're moving in the positive direction when the velocity is positive. So that is here. We can kind of see from the graph, it looks like it's from 0 to 1. They're moving in the negative direction down here after 1. It looks like, now we can verify those things, and we would if we were working this problem by saying, all right, I want to set v of t equal to 0. And so I'm going to factor out 2. I get t squared minus 4t plus 3. And if I factor that, I'm going to get t minus 1, t minus 3. If I set that equal to 0, I see at t equals 1 and t equals 3. Those are my 0 points. And since I'm going from 0 to 3, I want to know, what does this thing look like from 0 to 1? And what does it look like from 1 to 3? Since I know it's 0. Oh, sorry, 1 to 3. And then, well, that's all we care about is 1 to 3. I know it's 0 at 1 and 3. So on 0 to 1, I would just plug in, say, 0.5 into this. And then the next, I would plug in, say, 2 into here and see what I get. And we would find that from 0 to 1, we're greater than 0. And from 1 to 3, we're less than 0. And so we look like so. Okay. All right. So next question, now that we've determined when we're moving positive, when we're moving negative, the next question would be, well, what's the displacement here? Okay, well, the displacement is the integral of the velocity function. And so we want to integrate the total displacement from, well, let's actually do it in pieces. So let's see, we know we go 0 to 1, we were positive. We know from 1 to 3, we're negative. And then let's look at the total displacement there. So the displacement is just the integral of the velocity function over the corresponding interval. So there, we're going to do the integral from 0 to 1, and that's going to be 2t squared minus 8t plus 6. So that works out to be, all right, t cubed over 3, so 2/3 t cubed minus 8t squared over 2. That's going to be 4t squared plus 6t, and this is evaluated from 0 to 1 for the first one. Yeah, that's just going to work out to be 8/3. The next one looks at the integral from 0 to 3 of the same thing. Okay, well, the antiderivative is going to be the same. Now we're just looking at different bounds here. Now we're going to evaluate it from 1 to 3. And if I do that, I get negative 8/3. And so the integral from 0 to 3 of v of t dt, well, I could just do the whole thing, do it directly. That would work too. But also, right, since I've chopped this into subintervals, the integral from 0 to 3 of v of t dt is going to be the same as the integral from 0 to 1 plus the integral from 1 to 3 of v of t dt. And so that's going to work out to be 8/3 plus negative 8/3, which is 0. So what does that mean then? Okay, what does that mean? How do we interpret that? Well, what that means is that the jogger from time equals 0 to 1 runs away from their starting point, and then they turn around and they run back to their starting point. Right? Just like my driving to the store, turning around and coming back home. Okay, my displacement was 0. I ended up at my starting position. My displacement was 0. Well, what about the distance? What is the distance traveled by this jogger over the interval 0 to 3? Okay, well, that's asking us to do the integral from 0 to 3 of the absolute value, the speed, absolute value of dt dt, or sorry, v of t dt. Okay, now we can integrate the speed and get these same results, but if we do the integral, the absolute value, then remember we have to figure out, well, on the portions of the interval where the equation is positive, we're integrating the function itself. Okay, so from 0 to 1, we're integrating 2t cubed minus 8t plus 6 dt. On those portions where it's negative, we're doing the negative of the function. So that would be plus the integral. I'll do this down here. You can see what I'm doing on my screen here. So that would be plus the integral from 1 to 3 of negative this. Now we already know each piece is 8/3. Without the negative sign, it was negative 8/3. So that is going to work out to be 8/3 again. So the whole thing is going to be 16/3 as the distance traveled. Now, going back to the definition, we note that to find the displacement of an object, I don't need to know where it started, right? So I didn't need to know where my object started to find the displacement of the object between t equals A and t equals B. Okay, for example, whether an object moves from -20, from s equals -20 to s equals -10, or from s equals 50 to s equals 60, the displacement is the same. It's 10 units. Okay, I integrate the velocity function over that time interval, and that gives me the displacement. I don't need to know where I started to know the total displacement. But what if I don't want to know just the displacement? What if instead I want to know the position of the object at some future time? Well, if I know the velocity of the object and the time interval in question, I can figure out the displacement, but I need to know that initial position to figure out where the end position is. So I know the velocity of the object and I know the initial position, s of 0, and I know the velocity of the object is v of t, and I know what I'm interested in is where the thing is going to end up. So, right, the integral from 0 to t of v of x dx, I know from the fundamental theorem of calculus, right? This is the integral from 0 to t of s prime of x dx, and that's just going to be s of x evaluated from 0 to t, which is going to be s of t minus s of 0. So solving for s of t, that tells us s of t is going to be my initial position plus the displacement between times 0 and t that I get by integrating my velocity function. And so that gives us, I was doing a little bit of that without you guys seeing because it was a little small, but here, this is what I was saying. So I know just from what we had before, the integral from 0 to t of v of x dx. Well, v of x is s prime, so that's the integral from 0 to t of s prime of x dx, Well, S is obviously an antiderivative for S prime, so that's going to be S of X between 0 and T. That's S of T minus S of 0. Solving for S of T, which is my future position at time T. That's my initial position, S at 0, plus my displacement. And all of that is what you're getting at in theorem 6.1. Okay. And theorem 6.1 is there's nothing new on it. It's really just a restatement of the fundamental theorem of calculus. Okay. It's just a restatement of the fundamental theorem that we learned before. So let's consider an example to apply this theorem. Suppose we have a block. This block is at rest, hanging at rest from a massless spring at the origin. All right, so S equals 0, which is hanging, sitting at rest. That's going to be the origin. And what we're going to do is we're going to pull the spring down 1/4 of a meter from the initial position. So S at time 0 will be -1/4, and then we're going to let it go. Okay, so S of 0 is -1/4. The velocity, once we let the thing go, is given by V of T equals, so you can see, equals 1/4 sine of T. Okay, where T is greater than or equal to 0. Okay, we assume the upward direction is positive. All right, does this make sense? Well, yeah, because the thing is just, the spring's just going to bounce up and down, right? It's going to go back above, then it's going to drop and back above and drop. And so naturally, it's going to be doing a periodic motion. We're going to make some assumptions like, no friction and all of that. So it'll just continue to bounce around like so. All right, so the velocity of this thing, 1/4 sine T. There's the graph of the velocity function. All right, so part 1. Part A is we want to find the position of the block for time T equals 0. So we were given V of T right here. We were told S at 0 was -1/4, right? And so we want to find the position function for T greater than 0. Now, then we want to graph the position function, and then we want to, and we'll answer some questions about it after we get it. So let's start with the first part. We can do this problem 2 ways. We're going to start with using antiderivatives. Given our position function, we can integrate V of T dt, just do the indefinite integral. So that's the indefinite integral of 1/4 sine of T dt, and that's going to give us -1/4 cosine of T plus some constant. Okay, all right. So this is, to within a constant, our position function. So knowing that S of 0 equals -1/4, if I set this equal to -1/4 cosine at time 0 plus a constant C, well, cosine of 0 is 1. So that means C has to equal, so this equals 1, so this means C has to equal 0. And so that means S of t has to equal negative 1/4 cosine of t. Okay. Alternately, I could use theorem 6.1. And theorem 6.1 says, okay, I know V, I know S of 0, and so my position function S of t is going to be S of 0 plus the integral from 0 to t of V of x dx. And so S of 0 is negative 1/4 plus the integral from 0 to t of 1/4 sine x dx. Okay, so that's going to be negative cos evaluated between negative 1/4 cosine evaluated between 0 and t. So that's going to be negative 1/4. Well, cosine of t, so that's a minus 1/4 cosine of t, and then minus a cosine of 0 is 1, so that's minus a minus 1, so that's going to be plus 1/4 times 1/4, right? So that's plus 1/4, so those cancel, and you're left with 1/4 cosine of t. And just remember, be careful. It's easy to make a mistake on the signs here. So let's look at what 1/4 cosine x between 0 and t means. It means negative 1/4 cosine t minus negative 1/4 cosine of 0. Okay, so be careful. It's easy to make mistakes with the signs in these things. Make sure you're right. This means this evaluated at upper limit minus this evaluated at lower limit. Okay, so those are the two ways to look at that problem. All right, so we started with the velocity function using either the antiderivative or the method or the initial or theorem 6.1, position from the velocity. We get the position function like so. And then we could use the position function to answer various questions. What would the position be at a particular time? When do we return to 0? Whatever the case might be. Now, if you recall for some previous chapters, remember the acceleration of an object was the derivative of its velocity function. And so that is just the second derivative of the position function. The relationship between velocity and acceleration is the same as the relationship between position and velocity. And so the change in velocity, v at b minus v at a, is the integral from a to b of v prime of t dt. And v prime is a, so that's the integral from a to b of the acceleration function. Okay, so that means that if I, just like with position, if I know the velocity and I know the initial position, I can find the position function for all future times. If I know the acceleration and I know the initial velocity, then I can find the velocity at all future times. And so here is theorem 6.2, which states the relationship between velocity and acceleration. Okay, given an acceleration a of t of an object moving along the line, its initial velocity v at time 0, the velocity of the object for future times is given by v of 0 plus the integral from 0 to t of the acceleration a of x dx. Okay, again, consequence of the fundamental theorem of calculus. So let's consider a little example here of an old artillery problem. An artillery shell is fired directly upward with an initial velocity of 300 meters per second from a point 30 meters above the ground. So maybe we have a cannon sitting up on a rock or whatever the case may be. If the only force acting on this thing is gravity, gravity produces an acceleration downward towards the Earth of 9.8 meters per second. The velocity of the shell while it is in the air is what we want to know. All right, so we know a couple of things. We know my initial position is s of 0, that's 30 meters. We know the initial velocity is 300 meters per second, and we know the acceleration is a constant acceleration of 9.8 meters per second down. So that would be negative 9.8 meters per second squared. Sorry, meters per second squared, not meters per second. All right, so we want to know the velocity of the shell while it's in the air. So we're going to take those things and we're going to say, all right, I know s of 0 is 300. Sorry, I know that's 30, not 300, 30 meters. I know my initial velocity is 300 meters per second. And I know the acceleration is constant. So a of t is constant, and that's a constant negative 9.8 meters per second squared. So the velocity at any future time t is the initial velocity plus the integral from 0 to t of my acceleration function. Okay, velocity at time 0 is 300. The integral from 0 to t of negative 9.8. So this is going to be negative 9.8 x evaluated between 0 and t. Which is negative 9.8 t. And of course, so this is meters per second squared. T is in seconds. And so this whole thing is going to give you meters per second. Okay. So the initial velocity, 300 meters per second, it's going to decrease from there. That makes sense. The only thing acting on it's gravity. Okay, nothing's pushing it upward. The only thing acting on it's gravity, so that's going to slow it down till eventually it stops going up and starts coming back down. Okay, so knowing this velocity function, I could graph this thing. Okay, so here's my velocity function. Well, now, Since I know the velocity function, v of t, I could apply the previous theorem. I could integrate the velocity function. I know the initial position, and so I can find s at time t by the initial position and integrating the velocity function like so. So everything that we've said about velocity, position, and displacement carries over to more general situations. Okay, and those more general situations, such as suppose I have some quantity Q that changes with respect to time. Okay, Q could be anything. It could be the amount of water in a reservoir, population of white-tailed deer in an area, the amount of copper that's consumed or produced by a country, whatever. If we know the rate Q prime at which Q changes, so if I know Q prime, or if you like dq dt, so if I know the rate at which Q changes with respect to time, then integration allows me to either calculate the net change in the quantity Q, or if I know an initial value for it, I could find any future value of Q. And the argument is the same as before. Since Q is an antiderivative of Q prime, the integral from a to b of Q prime of t dt is Q at b minus Q at a. In other words, right, the net change of Q over the interval AB. Okay. Geometrically, the net change in Q over that time interval AB is the area, the net area under the graph of Q prime over the interval AB. So the product, Q prime of t dt, is the change. Q prime of t dt is the change in Q over a tiny increment of time. And so what we're basically doing here is, if I have the change in Q over a tiny increment of time, that integration says I'm just going to add up all of those tiny changes, right? Integrating Q prime accumulates or adds up those small changes over the interval AB, and the result is the net change in Q between t equals A and t equals B. So rearranging this, we get the net change and the future value for any quantity, not just position, any quantity that changes over time at a known rate Q prime. The net change in Q between t equals A, t equals B is Q of B minus Q of A, which is the integral from A to B of Q prime of t dt. And if I know an initial value Q at time 0, the future value at any time t greater than or equal to 0 is Q at 0 plus the integral from 0 to t of Q prime of x dx. Okay, so the more general theorem. Okay, now we can roll everything together into the following table for velocity displacement problems. Position s of t, velocity s prime equals v of t, displacement, the integral of velocity in the future position, the integral of velocity plus the initial, and that extends to general problems. Anyway, volume, population, whatever Q is, if I have the rate of change, the net change is the integral of that rate of change, and the future value is given by that integral plus the initial value of Q. So to finish up with an example, suppose we'll do an example of production cost. Suppose a publisher estimates the marginal cost, C prime of X, of a particular title in dollars per book is given by 12 minus 0.0002 times X, where 0 less than or equal to X less than or equal to 50,000 will be the number of books produced. And we want to know the cost of producing the 12,000th and first through the 15,000th book. Okay. Now we recall from section 3.6 that the cost function, C of X, is the cost required to produce X units. The marginal cost, C prime of X, is the approximate cost of producing one additional unit after X units have been produced. And so the cost of producing books 12,001 to 15,000 is the cost of producing 15,000 books minus the cost of producing 12,000, the first 12,000 books. Therefore, the cost in dollars in producing, and this, right, we should state this C at 15,000 minus C at 12,000 is going to be the integral from 12,000 to 15,000 of C prime So this is the integral from 12,000 to 15,000 of 12 minus 0.0002 x dx. That's a straightforward integral. 12x minus 0.0001, because it's going to be 0.0002 divided by 2, right, x squared, and we evaluate that between 12,000 and 15,000. And that works out to be $27,900. Okay. All right. So that's it for this section. Next time we'll do the very last section of the course and we'll finish up.